which is, I really believe in the Bayesian philosophy, but I don't think we're there yet for deep nets. And I'd like to further understand where the discrepancy is and how we can get there. And then, from a pragmatic point of view, I think it was you, Andrew, who was also chiming in about ensembles online. And, from a practical point of view, like, how can we come up with practical ways to get good uncertainty, and then really ground those either very strongly empirically or in theory. And so I think there's a lot of interesting work to be done in that direction. And then finally, I think we know a lot about what works well in the limit in the ideological sense. And so then it's a lot about how do we approximate these techniques that we can't actually bring to bear on these huge networks and large data sets in a way that's tractable and useful.
Yeah. I just want to add a few thoughts. I think I agree with everything Dustin and Jasper said. To me, I think we are just getting started in some sense, and right now we are kind of like still trying to figuring out what are the kind of like ingredients that we need to build, like neural nets that know what they don't know. And right now, taking a step back, the way I think about it is like there is stuff about what we want to, like the single model uncertainty setting. I think that's kind of like an interesting direction, and this is still a lot more to be done. And in terms of like ensembling, and I think Dustin presented a lot of ideas on efficient ensembles and how we can interestingly share parameters and using insights from loss landscapes and optimization of neural nets to design more compact ensembles, which will pave the path to scaling ensembles better in some sense. So I think that's also a very interesting direction. And the third is expressing inductive biases in terms of data augmentation is one way to do it, but there's a lot of ways we can express inductive biases on like functions and so on, and that's also been like very powerful for improving performance. So I think once we get a sense for how these models do on like common benchmarks, I think like I mentioned in my tutorial, the part, like I think uncertainty and OOD robustness are pretty much at the heart of a lot of things that we do in machine learning, right? Like so open set recognition, decision making, active learning, continual learning, lifelong learning, reinforcement learning, and so on. So I think once we have this better, we obviously there are some, for each of these you could think of applications. So I think Dustin mentioned like healthcare and maybe like decision making. So those could be some applications, but there's also a lot more, even in like research ideas, using these ideas to knowing when to trust models, and even in like, reinforcement learning, for instance, like I spoke about like a few in the talk, but also you can think of this at the heart of so many things. Like when you do backup updates, you can use the uncertainty to know when to trust the estimate and which backup estimate you trust more, and so on. So there's a lot of open ideas here that we can kind of like explore.
Hello, I have a question. Can you hear me? This is Ranganath.
Yeah, we hear you.
Hey, hi Dustin, Jasper, Balaji. Thank you for the awesome tutorial and all the great work that you do. I have a question on how to evaluate uncertainty calibration for regression tasks. In the tutorial, you did cover on the metrics like expected calibration error and negative log likelihood and bias score, right? So for the regression tasks, how do we evaluate we are obtaining well-calibrated uncertainty bounds, and do you have any plans to include a regression task in the uncertainty baselines?
I can maybe start if that's okay. Yeah. So great question. So for regression, you can actually define similar calibration measures. You can look at like reliability diagrams. Like for instance, a simple thing that you could do is if let's say your model predicts like a mean and a variance, you can convert that into like a binary task in some sense. So you can define like 10% confidence intervals, 20% predictive intervals, 90% predictive intervals, and so on. And given test data, you can actually see what fraction of the times the observed value lied within each of these estimates. So you can take 10%, it's a slightly different notion than what we do for classification, but you can do reliability. There are versions of reliability diagrams and so on for regression, and you can do pretty much all of the metrics. Right? So there are also another common way in the scoring rules literature is what's called cumulative ranked probability score, which are basically once you convert you can define losses on CDFs basically directly, and there it's kind of agnostic whether you do classification or regression, because once you move to CDF land, you can define these quantities and you can measure calibration. So we will. That's a great question. I'll add some references in the slide deck. We are trying to collate some references at the end for people learning more. This is one of the things I will add there as well. Thank you.
I also wouldn't discount sort of like synthetic regression sort of examples. I think in statistics, for example, the common way that you assess how good your confidence interval estimates are exactly doing multiple replications of an existing data set that you know, that data generated maybe fit to like maybe a model that's fit to another data set, and then that's the way that you get your synthetic data, or you know, any other strategy to get multiple samples effectively.
Yeah. I actually, in our paper tomorrow, if you're interested, I can give some references there. We did like a synthetic regression task, and we are also planning to add that to a baseline code base at some point. But there is an example of regression dataset with dataset shift, and we use this in the Bayesian deep ensembles paper. So what we looked at is you train on one split of the data, and then you evaluate on progressive dataset shift. And you can measure like how the you know, negative log likelihoods vary through time, how does the mean square error vary through time. And in classification, we do confidence versus accuracy. You can do something related where you look at the models. You can think of like the model's precision, the inverse variance as a confidence, and as measure of accuracy, you can look at the mean square error. So in the paper, we did like versions of these for regression as well. I'll add a link in the Zoom Q&A.
Thank you. I will take a look.
Hi, can you hear me? This is Akshay.
Yeah, we hear you.
Hi. So in the talk, thanks for the talk, by the way. It was a great learning experience. So I just wanted to know, in terms of robustness, the main types of robustness that we saw was related to image corruptions, the common type of corruptions that we see. Do you think these methods could, even like the methods that we discussed, could be applied to something like adversarial robustness? Have we seen works of that regard? And yeah, just wanted to see what your opinion was on that.
Balaji, maybe you're the expert on this.
Okay, I can take this. Feel free to chime in later if you want to add. So, so we have looked at a bit of like the ideas from adversarial training and so on. So in fact, actually, I used adversarial training in the deep ensembles paper. And that was actually one of the things we found to improve robustness of models. So the way I kind of think about it is, you can think of adversarial distributions as kind of like worst case OOD in some sense, right? Like, because you use the information about like the model and to fool the model, and it's kind of like a worst case behavior. So in my opinion, we focused a lot. There's a lot of people working on adversarial robustness and improving, and I think a lot of those ideas would translate to OOD robustness as well. So I think methodology-wise, I think there's a lot of interesting interplay between these, and we have done some work that's under review on this along these lines as well. But that said, I also believe that you don't need to necessarily be adversarial to encounter these kind of like OOD robustness. So we focused a lot on, I gave a lot of examples where there's natural distribution shift. And even in those cases, these are not solved. So philosophically, I started focusing a lot more on OOD robustness question, mainly because the worst case of all methods could be really bad, but the average case could still be much better, right? Like, so this is kind of like the philosophy behind randomized algorithms and a lot of algorithms research as well in other parts of computer science. So I think we should probably, even if so you can think of this as a kind of like a simpler problem in some sense than adversarial robustness. So
yes,
you can't even solve this task it may not make sense to talk about like the worst case behavior and so on. So a lot of our research so far has been focused on OOD, robustness, and identifying natural distribution shift, which are also more commonly encountered in applications than, but adversarial robustness is also encountered in some security applications. But so it's clear that we need more work there as well. But I think we need both in some sense. So
I would definitely plus one the general theme of thinking about adversarial robustness or adversarial training as effectively worst case analysis. I would also just shout out like two other works that I think are super relevant in sort of intersection. There's one on in the conference about like do adversarially robust models transfer better. And there they actually had a very, as I was reading the paper, I think last night, I was surprised by how much of their narrative was very similar to our sort of division that we were sort of laying on the tutorial, and that this is that the thing you're doing with adversarial robustness is effectively imposing a specific type of invariance that your models are trying to make invariant predictions that are not susceptible to imperceptible changes to the specific example. And the imperceptible change is according to the maximal, LP distance that you're perturbing from the example. So that's one thing you can do with adversarial training, and I think is something you can definitely look into, either if your task is specifically natural distribution shift or adversarial distribution shift. Another example of this I think is interesting is instead of thinking about just adversarial training on the data space where you're perturbing inputs and outputs, I think there was another work in NeurIPS that was thinking about sort of adversarial weight perturbations.
Weight perturbations, yeah. Mm-hmm.
Yeah, I thought that one was pretty cool, and that that also connects to some interesting work on generalization theory, where among generalization measures that tended to perform really well, there was sort of a slight dichotomy between approaches that were more pack-based and that they're doing expectations over given perturbation over a specific loss surface, so perturbation over the weights, versus taking a specific direction in the weights and such that like this is more sharpness based rather than sort of covering the entire area of that mode. And I think there's some works, there's the adversarially robust one that does this. There's also work that I was looking at called like sharpness based minimization. Taking the idea of a worst case analysis explicitly for training, so it'd be kind of like a Bayesian neural network or something where you're doing expectation over the weights, but instead of expectation, it's a supremum that you're then differentiating over. So I think that there's tons of ideas that are ripe in that intersection.
Thanks for that. I'll look into this.
Hi. Oh, thanks. Yeah, I have two questions. Once again, thanks for the tutorial. I asked one question. So basically, based on the motivation in order to have better and fast approximate inference methods, have you ever thought about that probably using quantum machine learning could help to fix this problem? Like thinking about that maybe we can have better and fast approximate methods. Yeah. And the second question is a bit different because it was not mentioned in the tutorial, but in the case for deep generative models, do you think that a possible way to fix this problem of OOD, it has to be with the problem of the typical set, or maybe something more difficult?
I can take this question.
Go for it, Balaji.
So for the quantum computing part, I'm actually not sure. I'm not too familiar with that literature, so I can't comment on that. Dustin, Jasper, do you have?
No, I can understand kind of philosophically why it seems exciting, right? The quantum idea is that maybe you can infer all parameters or like all models at the same time and compute the marginal likelihood in Bayes' rule in one step. But how to get there, I have zero understanding.
Yeah, and I think there are like huge implications of it. Like I think, for example, the entire idea of how we formalize causality is largely based on Newtonian mechanics, and it's mostly simplification, where there is there's effectively this like known phenomenon called the Blosses demon, where if you assume that you know all states in the universe and maybe their velocities, then you can deterministically simulate the rest of the universe, because you can precisely map, you know all the unknowns, and you can precisely map to perform deterministic and perfect predictions. But if there's inherent randomness, then that's maybe not the case, and that might tie, for example, closely to aleatoric uncertainty, whether or not you can truly reduce all of the uncertainty in this specific data point just by observing more and more features about it. But for the overall field of quantum machine learning, I am maybe not the right expert for that.
Yeah,
thanks.
For the other question on deep generative models and typical sets, that's actually a great question. We unfortunately couldn't get into this in the tutorial, mainly because there's just like so much exciting work in the field, and we didn't get a chance to unfortunately go into so much detail. I'll add a reference here, but the short answer is we have done some work on understanding why deep generative models, this kind of like surprising behavior on when they can assign like higher likelihoods to OOD data and so on. And precisely on the typicality, we have a paper basically showing that you can devise a test and that works better than just looking at the likelihood. So I'll add a link to the paper, and we have some recent follow-up work as well, which builds on the typicality idea and using like an alternative hypothesis test for better OOD detection in deep generative models. So in the tutorial, mainly we focused on assuming that you use the model probabilities themselves and how to improve that. So it's mainly focused on like uncertainty quantification in discriminative models, like P of y given x models. But there's, I think, modeling the joint, like P of y comma x, and using generative models, the initial results were not so promising, but now that we've understood why this phenomenon is caused in like deep generative models and so on, and now we can go back and investigate other approaches for building better hybrid models. So I'll add a link to a presentation that I gave a while ago on this topic, but yeah, I'm happy to provide more references if others are also interested in this.
Right, thanks a lot.
So I think Aditya was next, if you wanted to re-raise his question.
Yes, thank you guys. It was an excellently put talk yesterday. Thank you for that. The question I had pertains to the domain of non-IID inputs. Basically, how do we translate the techniques you describe to autocorrelated inputs such as time series, especially, I guess?
Yeah, that's a great question. So I guess the question may be like, can we ever guarantee that we will get reasonable uncertainty on out of distribution data, where out of distribution, I guess, could be arbitrarily far from our input data, our training data. And the answer there is tricky. I'm not sure that there really is theory to guarantee generalization beyond the IID training set. And thus, I think often we kind of reason about it as saying, okay, well, if the IID training set was generated from the same distribution as the global data set, there's some larger distribution and the training set is some subset of that, then there's some model that fits both the training data and the data that you want to extrapolate on well. And in my view, that then justifies the idea of marginalizing over lots of models or all the models that fit your training data well, and then reasoning about the fact that you don't know which one of those models, the one that extrapolates in different ways, is the one that corresponds to the one that generates this kind of later out of distribution data. And so in my view, the answer is we should be marginalizing over models to get that uncertainty away from our training distribution. Do you have things to add to that, Dustin and Balaji?
No, I think doing uncertainty for like sequence models in general, whether they're you know, they're either discrete time series models or kind of continuous time series. I think a lot of the things that we applied are effectively the same. If you think of, if you're sort of modeling on the input as like any, as you might bag this as a specific, you know, huge array or something that you're modeling per time step and you're trying to return a specific output. There are, of course, still things that you have to consider regarding like how you might measure calibration on, you know, outputs that are not just scalar valued. I think there's, you know, some interesting work around those areas. Log likelihood is always applicable.
Yeah, I think this is a good question, and actually this goes back to the bigger question of how do we actually define OOD, and right, like, so it's particularly challenging, like within a sequence. So I think that on the topic of whether if you think of like sequential data as a modality, we have done some work on, like, you know, some kind of like sequence classification tasks. Like, for instance, I pointed at this genome sequence classification where it's also a way for us to make sure that the techniques we develop don't overfit to like connects or something, right? So there, but again, like, it's like at the sequence level, the classification is at a sequence level, but not within a sequence. And obviously in text as well. And Andre here has also done a lot of nice work on uncertainty in structured prediction tasks and so on. So I think this is still like a early days in this line of work. So I think more work needs to be done to do like better uncertainty modeling for these setups.
Okay, thank you, everybody.
Thanks. Just going through this list, looks like Vikash unmuted himself. Feel free to raise your question.
Sure. Hi, this is Vikas from Princeton, and yeah, again, thanks a lot for the tutorial. There was a lot to learn actually. My question is, it's more of like a, I wonder what your opinion is on this, like in the direction of out of distribution detection, but now thinking from a perspective that we don't assume that we have fine-grained labels available for the in-distribution data. So kind of like going back to the classical outlier detection setting where we assume that we just get like this pile of data and often even corrupted with outliers. So it's like even going beyond fine-grained labels. It's like, how do you like learn this notion of what is in distribution just from this very unstructured, like not like a well curated data in a way.
So I have some opinions about that I think differ from maybe my colleagues in this chat. My perspective is that, like, ultimately it doesn't really matter if whatever example you're predicting is in distribution or out of distribution. So I'm a huge advocate of calibration error, which is ultimately a function of a model and the distribution you're assessing it over. And it doesn't matter what the model was effectively trained on. I think ultimately maybe the most popular use case of uncertainty is deferring predictions, and the ability to defer predictions does not matter if an example you're predicting is OOD, for example. As you were noting, anomaly detection, which is slightly different from out of distribution detection, is all about outliers that are unusual with respect to the distribution you typically train, the data you typically trained on. So, you know, an outlier might be in distribution in that it's like, you know, 3 standard deviations that are a sample from a normal distribution, for example. So I generally recommend like that all you should assess is that downstream performance. So if it is a deferred prediction, that you should assess how well your model performs on that deferred prediction task. I do think that OOD detection is an important area. I think there are examples where you do want to determine if in a specific, like over a specific prediction. So for example, there might be a service that is trying to, you know, perform a specific task like an assistant, and it and you get a bunch of requests, and so certain requests might be out of scope, and you want to specifically say that you're out of scope, even if you can predict well on that specific request. But I think in the majority of cases, if you're just deferring predictions, it doesn't matter.
Yeah, I think it's worth adding that so I agree with Dustin. I think it's worth adding that maybe part of what you said was that you could have outliers and you could have noisy labels and so on. And maybe one thing that we didn't really talk about a lot in the tutorial was like, how do you actually deal with aleatoric uncertainty, even when you're training? And that's often done in the likelihood function, right? So if you were doing a regression with squared error, then you'd have like a Gaussian likelihood. But you may intuit that there are outliers in the training set, and that corresponds to a different noise model, basically, right? And then you could use a student T distribution as your likelihood, and that's a little more robust to outliers in the training set.
I think that also relates well to a question that Augustine raised in the chat. If you have the ability to speak, feel free to raise that question.
Yeah, thanks. Yeah, thanks for the tutorial. So I'm working on sort of exploration in stochastic environments. And in these sort of applications, you really want to go after the epistemic uncertainty and, you know, try and avoid aleatoric uncertainty to get good exploration. But I find in practice, this isn't always very easy to do. So I was just wondering if you had any opinions or tips on this kind of thing.
Yeah, I mean, I definitely I played around with the kind of the Atari Q learning models for a long time, believing that like proper uncertainty model would do better in that regime in terms of exploration. And also wrote a paper on contextual bandits with Bayesian neural nets. Similarly, feeling like better uncertainty led to better exploration and thus better reward downstream. And I still believe that philosophy is true, but there are so many things going on in these scenarios. I guess when you have multiple decisions and some downstream reward, then the notion of uncertainty is conflated quite a bit, and you can explore too much or not enough. And so getting the right amount is tricky, to say the best, or to say the least. But I think it definitely helps, in my view, to have a better model of uncertainty. And so if you're using like deep networks for this, you may think of using ensembles, for example. And I think that can only give you strength, because then you're not committing to a single model hypothesis, right? But you're kind of hedging your bets across multiple models. The same is true with Bayesian deep learning models. What do you think, Dustin and Balaji?
I can maybe add, but and also to on Vikash's earlier question on OOD detection. So I'll first answer the OOD detection part. So I think, if I understand correctly, your question was about like the OOD detection well defined and how do we make progress there. I think if you look at there's a lot of methods being published, and it's clear that even with an OOD detection, you can imagine some pairs of data sets being much easier to separate than, say, for instance, other pairs. We initially proposed this at the time because, this was just like easy to do and like an easy example for like a lot of people in the community can easily replicate this setting. But it's clear that, like, for instance, even within this OOD, you can imagine there are some examples of like near OOD, which are classes which are quite similar to your training classes, and somewhat further OOD, which are far away. So as a concrete example, maybe like if you're doing CFA10 classification, SVHN might be like far OOD because the class overlap is much further away, whereas CFA100 could be like near OOD because it's also like the classes are maybe similar and it's harder. And obviously, the closer and closer the distributions are, the harder they may be to separate, and it's a harder task. So I do think it's important to, now we have a lot of reliable methods for doing far OOD detection, so that we can now focus on more on the near OOD setting and making progress there. So I think that's one thing. And also tying this back to the applications point that I think Dustin and Jasper are talking about, one of the complications has been for OOD detection is lack of benchmarks that kind of are realistic in the sense that they capture the kind of thing that we want in application. So I think that this is actually one of the points we also mentioned in the tutorial. We clearly need like more better like realistic OOD detection benchmarks to also, data sets are very important to inspire research. And I think the out of scope example Dustin mentioned is a great example. We also open source this genome sequence classification, where we also know the kind of like, based on like the phylogenetic tree, you can know which classes are close, which classes are far away, which gives a sense for what tasks or which OOD detection is hard and which is difficult. And we hope that more people start using these benchmarks and also create like newer benchmarks.
Yeah. Thank you for the answer.
And for the other part, on the distinction between epistemic and data uncertainty, this is actually very, it's one of those things, I think it sounds nice in theory, but it's very hard to do in practice, mainly because it conflicts like a lot of things about like our modeling assumptions and so on as well. And it's kind of hard to pin this down. On a more philosophical level, I kind of think this thing is, this distinction is, I agree that this distinction is super important in applications like, exploration in RL or even active learning, because you want to focus more on the reducing epistemic uncertainty if you really believe the other is irreducible in some sense. I think philosophically, there's also, you can argue, given how much it ties into like modeling assumptions, it may be actually very hard to separate out these two in realistic setting. I think the place where there's been some work on kind of trying to do this is, if you only model the conditional, I don't think you can actually do this, and you can come up with some counterexamples for why the partial observability makes it very hard to actually distinguish these two. But perhaps in my own research, my thinking has been that maybe if you actually do joint models, like hybrid models, which model the joint P of Y and X, then you can perhaps, even with a single model setting, you may be able to address this distinction, mainly because you know that if P of X or some notion of like, how many points you observe in this region, that could also provide some signal on decomposing the two types of uncertainty. And this was kind of like the inspiration for the hybrid models paper. But it turns out that the intuition is right, but the P of X is not the right measure for, there's a lot of data in this region. So and some other work has, in follow-up work, we have subsequently devised better ways to distinguish this. But I think that could also be a promising direction precisely for this application. Yeah.
Thanks.
I think Nicholas had raised the question very early in the Zoom meeting. Do you maybe have a chance to, raise it?
Yeah, hi. Thank you for your talk. It was really nice and interesting. So in our lab, we're working a lot with conformal prediction, and it's something that really works nicely for calibrating the models. But I don't see it too much on the internet and on many papers. It seems that it's like an alternate path. And I would have wanted to know what's your opinion on conformal prediction, since it's easy and performs well.
Yeah, that's a great question. So I actually have a paper submission with a couple of colleagues from Harvard into iClear on using conformal intervals for our benchmarks on CFAR10 and ImageNet-C and so on. And it certainly works well. That paper almost certainly won't get in, unfortunately, but I think the reviewers didn't find it particularly exciting. But yeah, I think, there is some stigma in the community around frequentist statistical methods. And, maybe we should be rethinking whether we should be using them or not. I think they are quite useful, and actually conformal inference is strongly connected to Bayesian inference, thanks to the von Mises theorem, right, which kind of bridges the two, or says that Bayesian methods will generalize well in the conformal guarantees sense. So yeah, I guess my answer is, I think I don't see why we shouldn't be using them. I think it would be useful to use these methods more.
I think as like in deep learning in general, we're extremely empirically driven. And to the extent that we define something that is abstracted as a benchmark with a specific task and a metric, any method that works well on that is the one that we will adopt. I think the community around conformal prediction is slightly different in terms of the things they focus on. But if they demonstrate, on these mainstream metrics and data sets, that these are the things that these are the ones that give you, highly calibrated, better calibrated models or better OED detectors, then I think everyone would just, strive to adopt that as the next greatest thing.
Okay, thanks for your answer.
So I don't know who's next. Feel free to unmute yourself and raise a question.
Hi, this is Chris Hain.
Oh, yeah, go ahead.
Thank you. Sorry to jump in. I work in clinical decision support, where due to privacy, we often assemble data from even different hospital systems. And our OOD is actually in the training data itself, and it's hidden from us. And certainly, we certainly want to convey to the physicians that are the customers of the models the uncertainty of the predictions. But how would you go about trying to address more the non-IID data that we're getting into and the risk of just predicting the source location or kind of instead? So thanks.
I can maybe start. So this is a fantastic question, actually. This is one of the things that motivates our calibration under distribution shift, in the sense that the populations of data from even like different hospitals could be very different due to other phenomena. Here's a case where we clearly need like robust models, and also doing more work on maybe non-image data, right? Like so electronic health records or other forms of structured data where we need like better uncertainty. So I think this is we are working on some techniques for investigating the robustness and uncertainty of models in this setting. And I think Dustin has been involved in some work in like uncertainty in medical records data as well. So maybe Dustin can add some pointers there.
I mean, I think one important one that's more of like an in distribution style type of robustness, it's more like closer to in the line like robust statistics, is like imbalanced data. So this like this often comes up, for example, in like studies around causation, but also just studies around heterogeneous data with imbalanced groups with features where you might have more data around a specific subgroup, like you might partition your data according to different ages, or there are certain minority groups that are just not as relevant and not as presently available in the data. And a lot of that literature is slightly detached from the literature that looks at an explicit shift in distribution that sort of and this is formally different in the sense that in one of them you can categorize it as X is drawn from P of X A train on, and others X is drawn from an alternative P prime of X or something. But both of them are extremely important. And I think a lot of the methods that we do develop that are assessed on out of distribution robustness are also extremely relevant for like more rare examples in the data. There are a few ways of trying to tackle this in terms of an explicit benchmark that assesses individual groups. So I think fairness literature especially is very relevant for that.
Yeah, I would say just one last point on this is one of the things that would really benefit more research in this there's also like better benchmarks that kind of like reflect these challenges. So if you know, like other data sets for investigating these kind of questions that can be open sourced for researchers, that would be fantastic.
Yeah, that certainly is a recognized issue. I think all the work on Mimic, right, comes from one hospital in Boston. So we definitely need a lot more data than that. So thanks very much.
Hello, can I ask 2 questions? Yeah, first, thank you so much for the excellent tutorial. My first question is related to how important it is for estimated uncertainty being Bayesian, exactly Bayesian. I'm quite interested in this because, as mentioned in the tutorial, usually ensemble methods works very well in practice, but in general, there's no way that they are being exact Bayesian, say even like epistemic Bayesian, except for very simple situations. Yeah, this is my first question. Yeah,
that's a great question, and I think we could spend the entire hour at least talking about that one. So I've definitely been having that debate online, kind of like during NeurIPS as well. And the way I see it is that the Bayesian formalism gives you, or gives us, a language to compose, specify, infer, and evaluate models. And there's a really nice set of theoretical guarantees and understanding connected to that, in such a way that you could, for example, plug a Bayesian model into a probabilistic programming formulation or program and just hit the button of inference. And since everything follows the same rules and is in the same language, ideally you should be able to just turn the crank and fit the model and then interpret it and get meaningful probability estimates and predictions out of it. The alternative of, okay, let's just get something that works well empirically in practice, it isn't composable, right? We can't like just throw an ensemble into a much larger Bayesian hierarchical model and expect to really understand kind of coherently that the scale of the predictions of the ensemble kind of correspond or work with the scale of the predictions of some other model, etc. And so the Bayesian philosophy, I think, really gives you this really nice language to specify and talk about and compose models, and thus it's really nice to adhere to. And of course, that being said, we basically can never actually be truly Bayesian for deep neural nets because they're too highly parameterized, except if we go the Gaussian process route. And then I think it's okay to be pragmatic and say, I just want empirically good uncertainty. And so I'm going to train an ensemble and then try to be as rigorous about validating that ensemble as possible, and then hope that it works well to extrapolate to out of distribution data, for example.
Yeah, I'll also probably add to that. I think there is a philosophical discussion which is also interesting from a scientific perspective on like what are the principles that we need for better uncertainty, right? Like, so there is this debate is much bigger than neural nets as well. So like, in statistics, there's a lot of discussion around like frequenters and Bayesians and priors and so on. So there's much bigger discussions that are also worth looking into if you're interested in this. From the neural nets perspective, I would say we need kind of both. Like, we need to theoretically understand the best working methods, but we also need to kind of continuously push, develop better methods, and sometimes the methods may be good enough, even though we don't fully theoretically understand them, or there's not like a precise Bayesian interpretation. And even like Jasper mentioned, in neural nets, it's very hard to be like properly Bayesian, because like anybody who thinks they can like marginalize over like a high dimensional space is either fooling themselves or just flat out lying, right? Like, so, and these are like well-recognized problems. Like mathematically, you can show that this is like a really hard problem to do without current computation and so on. So I think the way I think about it is we need to continuously push the limits of like develop methods that work well in practice and with neural nets and understand that, and also continuously tie it back to the principles as well. So I actually linked to like a discussion, and we have a poster tomorrow on relating to this as well. So the way I at least think about it, when we wrote the deep ensembles paper, the first thing a few years ago was it was kind of like a surprising finding that such a simple baseline actually works like more fancy methods, which require a lot more effort to implement, right? Like, so I think as scientists, we need to also be honest, and we need to take a look if a more fancy method does not work well. So what are the reasons? Like maybe one of the assumptions is being broken, and that's probably work back through your chain of reasoning and figure out where exactly this issue arises, and what is the wrong assumption that you're making. And I think in particular, so there are kind of like two issues. So one is there's Bayesian inference is principled and optimal only if you believe your model, you are operating in the right model class, and you can compute the true integral. So if you can't do both of this, kind of all bets are off, right? Like, so you can say approximately Bayesian, but that is not actually saying much. The quality of whatever uncertainty you're getting really depends on the quality of the posterior approximation. So, and in particular in neural nets, so the one way that I thought we wrote a paper last year on deep ensembles loss landscape. So if you think from a loss landscape perspective, basically what's happening is a simple way to think about neural nets and what they like variational Bayesian neural nets, why they don't work as well is, if you think what SGD does through the trajectory, a lot of tricks that we add from optimization perspective, like learning rate decay, regularization, and so on, the name of the game is really to make sure the neural nets converge in optimization and don't overshoot. And if you think about functionally, what's happening is, as through the training trajectory, what's happening is within a single trajectory, the model is going to explore fewer, in function space, it's going to explore a smaller and smaller space. So within a trajectory, and we have some plots in the deep ensembles landscape paper showing exactly this, that if within a single trajectory, the model explores fewer and fewer functions in function space. And if you fit a parametric approximation to this, then obviously it's in function space, it's going to be just capturing like one more of the posterior, right? Like, so if you think from that perspective, it's kind of like obvious in hindsight. And so what you really need to do is have some mechanism that explores multiple modes through like different parameterization. And I think Dustin has been leading a lot of work on these efficient ensembles and kind of like designing better architectures where you can simultaneously explore multiple modes. So there's a line of work there. And also, I think the neural tangent kernel literature in the kernel limit gives like a very interesting way of also characterizing what are these objects. So in particular, the paper we're going to present tomorrow actually shows that, it shows a very interesting result, is that if you look at from the infinite limit, deep ensembles actually do a pretty decent job at approximating the posterior mean, but they still don't approximate the posterior variance that well. And there are some simple cases where you can, and we propose a fix to the problem. It's a bit theoretical paper, but I think it points to the posterior object and how do we get samples from the exact posterior so we can actually do a Bayesian deep ensemble.
Yeah, thanks a lot for sharing your insights. My second question is exactly following what Balaji just mentioned about the mode in functional space. Because like, as you mentioned, it's very likely that if we just do Bayesian neural networks, all the optimized uncertainties and variations in the parameter space all falls into a single mode in the functional space. So it's important to have a well-defined sense of distribution over the functional space. Regarding this topic, beyond Gaussian process, are you aware of anything else that like mathematically grounding and well-defined regarding even what is the measure of a functional space?
Yeah, sorry, I was typing in the side panel while you were asking that, but my understanding of the question is, are there other methods that think about deep neural nets in function space as opposed to in
or just general measures distributions over functional space? Of course, Gaussian process is a well-defined thing that relies on on the intrinsic nature of this stochastic process. But other than that, even how do we characterize a distribution over functional space? And then the next question, of course, is how can we do VI on that, maybe? But beyond Gaussian process, are you aware of any tools or language to describe this problem and approach it? Yeah.
So I think there is some work in reasoning in function space, and we added some links in the tutorial slides. The other way you can also think about it is, you know, like Dustin mentioned, there's even like data augmentation and the kind of like invariances, the architectures, and every modeling choice that we make, there is an implicit, it corresponds to some implicit inductive bias that we are expressing in terms of like the functions that this can model, right? Like, so you could also think of them as kind of like indirectly specifying a prior over like the function space, and you can think through that lens.
Yeah, heuristically and implicitly, we can think of a lot, but I mean mathematically, something explicitly, other than Gaussian process, are you aware of anything else that is well defined there?
I mean, I think most Gaussian processes apply. Like, there's work extending Gaussian processes to student T processes. I think even in the Radford Neal like 1994 paper, there is work around like alpha stable processes. My general sense of like whether these are useful in terms of performing well on a particular benchmark is that it tends to be fairly open. I think in general, it's useful to disentangle the two key elements here, one of which is like what sort of input-output relationships do you care about? And another aspect of it is sort of the probability distribution aspect. In other words, do you have a sense of where probability mass should be assigned to enforce that sort of behavior? On one side, if you're just trying to enforce specific constraints, then you don't really need the softness that probabilities add. So more things like equivariant architectures, data aggregation is perhaps more relevant. However, if you do have some prior knowledge that maybe you want to encourage, you have a set of invariances, but you want to encourage one particular one more explicitly, then soft assignments like probabilities can help you. But in general, I'm always a fan of simple methods, and then sort of as you require that complexity, you start to add that type of machinery.
Yeah, if I understand your question, I think most people focus on the Gaussian process, but I would add that even that it's like a huge field, right? Like, so like just in neural tangent kernel, there are probably more than 100 papers written this year around like analyzing the kernel, because the Gaussian process machinery is too broad. It's mostly about like the kernel specified corresponding to architecture and all these things, right? Like, so I think there's a lot of design choices that you can do even within that, and a lot of people are looking at extending it to like different architectures, like and like investigating more in the finite width limit. And there's a lot of work on just like understanding neural net optimization through the lens of what's happening in like function space. And I think there's a lot of exciting work in the neural tangent kernel literature.
Thank you so much.
Hi. So thank you very much for the excellent tutorial. It was very, very interesting. I had a couple of questions. The first question is related to this maybe was not directly a point that you touched during the tutorial, but you mentioned it in the Rocket chat. So I don't know if it's okay to ask otherwise. If I'm off topic, just let me know. Anyway, the point was, so out of distribution with finding out of distribution inputs using generative models. Okay, you, Balaji, have done a lot of work on that. I wanted to ask if you think it makes sense to say that the main reason why these methods fail, okay, could be said because we really want a probability, while instead the method gives us a probability density. Okay, so the probability density can be very high, but the input can be completely unlikely. For example, for a multivariate, Gaussian distribution with zero mean in very high dimension, the maximum of the probability density function is at 0, while instead the most likely outputs from these most likely sample sources from this distribution, definitely they are not close to 0, especially as the dimension. So do you think that this could be a problem, the fact that we look at the probability density function while instead we should look at the probability of a certain input given a model? Or it's unrelated? They fail for some completely different reason.
I can answer a part of that. Maybe Balaji can also chime in. I think one thing that I think I agree with you in sort of that there is an important distinction there, which is I think a word that Balaji uses a lot is sort of typicality versus the probability density, which I agree with. And I think the ultimate distinction is that you're operating on sets. So one distinction, for example, between anomaly detection or outlier detection and out of distribution detection is that in out of distribution detection, you're determining if two sets of examples are different in terms of distribution. So training data set and a test data set. And then anomaly detection, it's about per example basis. Is this something that is an anomaly according to whatever definition you define an anomaly is? I personally think of any type of style of OD detection like that as effectively a two-sample hypothesis testing problem. A model, like a generative model, is effectively just a way of memorizing a given data set in that two-sample process. It's a training data set. And then you're using that specific function to determine how you might actually say if this other set of samples is actually different from the other set of samples. I think using probability densities or using initial typicality are different ways of doing that, but there are many approaches in the general hypothesis testing literature that I think to some extent has been tested, has not been tested. But I think that general lens of it is more important than saying what's the density of this given set of samples.
Okay, thanks.
Yeah, I just want to add, like the slide that we kind of we have some results there. I think the short answer is there's still a lot more to be done to understand precisely why, to understand the failure mode in a lot of detail. And one aspect is what Dustin mentioned, which is if you really think about it, like defining OOD for a single point is kind of ill-defined from a statistical perspective. So once you move to the set, you can actually define like divergences, distributions between some sort of like distance between distributions to kind of like quantify to make it statistically more principled, and we can get a handle on these questions. Like a simple counterexample that we had in the typicality test paper is, imagine you train a model on MNIST once, on all of MNIST, and a test set you only observe like MNIST once. Is that OOD? Statistically, it's a different distribution, but it's kind of like one of the modes probably of the in distribution. We can create a lot of like interesting edge cases that could still technically be OOD or a different distribution than the one you trained on, but how do we kind of like handle this question and so on? So there is that. The tying back to the inductive biases, I think there's been a lot of interesting work in the community on, like, I think pulling I think she presented a paper this at NeurIPS on OD detection for flows. We have some work investigating this for like autoregressive models, what's going on and so on. So there's still a lot of work in progress, and I don't think there's like a unifying theory that explains all of these yet, but should happen soon.
Okay, so just two last questions. One, if you could write the name or of the person you said that wrote Anomaly that is presenting a NeurIPS paper on Anomaly Detection. Okay, thanks. And second question, so if I understand correctly, Dustin point on your point, you said that anomaly, that out of distribution detection for a single point is ill-defined because the probability of a single point is always 0. Right? Or maybe I misunderstood. Instead, when you have a set, is no more, the measure is not 0 anymore. Not really.
I can answer the second point, which I remember, but I don't remember the first point. On the second point first, I think the argument is that if you look at the probability of a single point, or like just a single point, there's no way of determining if this is out of distribution, because the entire notion of a distribution is based on samples from a population. So you have no notion of what the population is if it's just a single sample. sort of the, one of the failure modes of probability theory in general, I guess.
Okay, thanks.
So just as one note, we are technically out of time. However, I don't think there's anything that constrains us from continuing this Zoom meeting. However, if you have other constraints, if you're, or this panel is not super interesting to you anymore, feel free to leave. But I think we could just continue to answer some more questions.
Yeah, I can keep going for a bit.
If I may ask a question, then based on the discussion before about loss landscapes, is there any theoretical problem with deep ensembles for in distribution prediction as opposed to out of distribution?
I think your question was like failure modes of deep ensembles for in versus out of distribution.
Yes, so I was wondering if there is any theoretical reason to believe that deep ensembles will not give you the right uncertainty in distribution.
I can maybe take this question. So I think one way to think about it is the base model, like P theta of y given x, whatever is the inductive bias of the single model itself. And ensemble, deep ensembles is just like one way to generate multiple theta. So it captures theta 1, theta 2, theta 3, and what functions we pick in like function space. So in some sense, the deep ensembles are really only as good as the choice of base model. So if you start off with a really bad model, in some sense, ensembling will be still better than using a single model, but it's not a silver bullet. It's not going to fix all of the problems. So we do really need to think about like, what is the inductive bias that we want to put in like any individual model. So one simple counterexample is on OOD, we can construct even like simple examples where ensembling may not fully fix the problem. And it's not to say deep ensembles are bad. It's basically deep ensembles are only as good as the underlying model that you start with. And we have a paper tomorrow where we discuss these failure modes and how to improve that better. I'll add a link at the bottom right now.
Yeah, I'd add the in distribution setting is one that I think the community understands a lot better than the out of distribution. And then you can appeal to things like empirical risk minimization or pack Bayes. So empirical risk minimization, right, says that, if you follow the ERM strategy, which is sample data from your training set and minimize expected loss, then if you have enough data from your training set, you cover it well enough, then you do have guarantees of generalization on your test set, provided it's from the same distribution. And there's no reason, I think, that ensembles don't also correspond to that. And then there's some really nice theory from pack Bayes. There's a paper recently from the last ICML from Andres Masagosa called Learning Under Model Misspecification, I think, that actually looks at the performance of ensembles on in-distribution data and puts down some nice pack Bayes theory to show that ensembles should generalize well under some circumstances to in-distribution data.
Thanks.
I see a couple of people raising hands. Andre, do you want to maybe ask the question?
Hi, yeah. So I had two sort of questions. One is a little more like low level. So so obviously, so it's about ensembles of regression models, and the question is, so when typically we have a probabilistic regression model, we have some kind of, let's say normal distribution, and so ensembling averages these normal distributions, which yields a mixture distribution. And when you do, for example, distillation of this, then you have problems. If you have one model which parameters a normal distribution, you minimize KL to a mixture, and you sort of have all sorts of issues. So one way you can mitigate this is with, for example, a geometric mixture. which yields also a single unimodal normal distribution. So what do you guys think about sort of not strictly Bayesian alternatives to combining ensembles, and how meaningful that is and how practically useful that is? So that's one question. The other question is about sort of accelerating ensemble inference. So I think a lot of work you discussed in your tutorial was about how you accelerate ensemble generation. But I'm not sure that those methods can make ensembles cheaper to use, like at test time. So so one approach is like distribution distillation, where you sort of distill an ensemble into a single model that emulates it, but it's still very expensive in generation. What do you guys think about methods of constructing models like ensembles, which are both cheap in construction and in inference, and whether such models can be constructed? Or perhaps perhaps ensembles are not the right way of going on about it. Maybe we should think in completely alternative directions.
Yeah, this is a great question. I think we've done some recent work. I think obviously distillation and ensemble distribution distillation is certainly one way to reduce the inference cost. But we've also been thinking about how to reduce the other strategies for reducing the inference cost. And I think, Dustin, do you want to add about MIMO next?
Yeah, so I can say something. I think on the aspect of resource efficiency, it's ultimately a question about what you determine the cost to be. So it could be at different time you care about memory budget less number of parameters, or at different time you care about like the actual inference latency or number of flops, or even maybe you're just constrained in terms of training. So there are a lot of things you can do in terms of budgeting things, and they all have different important applications. And I completely agree that for many cases, it is also about runtime efficiency. So the amount of milliseconds it takes in wall clock time to make the ensembled prediction. And I think there's a lot of interesting works there from, I think the spectral normalized neural Gaussian process work tries to capture uncertainty in a way that doesn't add too much additional compute. The MIMO work does this. And I think there's the literature that we're also talking about in terms of data augmentation is all about, and temperature scaling is all about not really changing the model so much and still improving calibration. On the aspect of distillation as a specific approach to improve sort of the costs, I think distillation is great, and it's a useful regularization strategy. I know that Zelda Marriott was looking into distillation as an approach to improve the overall diversity of ensemble models. So you might use an ensemble as a teacher model, and for a student model, it could be a deterministic model with like a multiple heads, or like a hydra, or it could be a more efficient ensemble that uses the teacher model as a way to improve the diversity, just because of the inductive bias to match towards those outputs. I think one of the conclusions from the experiments that she was doing was that it wasn't super clear if you needed the ensemble as a teacher model. There are a lot of things that sort of conflated improves in performance distillation, like the fact that just the teacher model might have higher accuracy. So whether or not these specific outputs you're matching towards with distillation, like if those even need to be calibrated to produce better calibrated ensemble student models. So I think there's a lot of open questions around using distillation for ensembles that isn't quite addressed yet. And I think that's a ripe area to improve that research efficiency aspect.
All right. Okay. Thanks. Thanks. Yeah.
Yeah, I added a link to the paper. I think there's a lot more work that we can do by leveraging like sparsity in neural nets and so on. That literature, I think we can do a lot more efficient ensembles as well.
There was also a question there about the first question was, I think, about how do you distill in regression if you have a multimodal model. And I think that we don't have a great answer to that. I don't know of a whole lot of work that does distillation for regression. I think maybe the Bayesian dark knowledge paper that Kevin Murphy was an author on. I don't know if either you, Balaji or Dustin, were authors on that. work. Okay. I think they distilled regression. But yeah, in the multimodal sense, I think it makes sense that you don't want to just compute the mean of the predictive distribution, but you need something more expressive. And that will correspond, I think, to like the distribution that you impose on the distillation model, right? So you could make it a mixture of some interesting kind. Yeah, I don't know of much work that has done that. I think it's an interesting question.
Yeah, I agree. I think we're just missing a good regression benchmark, and I think there's some interesting works that try to push more on that aspect of it. You know, I think that there's flight delays data set that's used quite often. I think it started from the large-scale GPU work that James Hensman was an author on. I know that there's also some work that we were doing with protein uncertainty, where you're given a protein sequence and you're trying to predict the affinity of the binding, or some additional property about the specific protein sequence that you might have synthetically created. A lot of those are effectively regression benchmarks, and a core part of protein synthesis is sort of decision making in a loop. So it's sort of like a Bayes-Opt sort of procedure of designing that sequence, and you can definitely just decompose that as sort of a one-step process of here's a batch of protein sequences that we have, and here's the property that you might want to predict, and what exactly what is the binding affinity, or what is some additional property of it. And yeah, I'm a huge advocate of anything that might give us a better regression benchmark for ground truth to answer a lot of these questions.
We have 3 more people who have raised their hands. Probably we should just take those 3 and stop there.
Sure.
Bertrand, do you want to go next?
Yes, sure. Can you hear me?
Yeah.
Yes, okay. So basically, there is this family of model which try to parameterize the Dirichlet distributions. And I was wondering, instead of the categorical distribution, and these methods are pretty fast, basically, because at training time and test time. So I was just wondering, what are your thoughts about that and your opinions? Do you think it's an interesting direction? Yes, this is it. Thanks.
Yeah, I think there's actually an interesting line of work as well. And I think Andre here did some of the work in the prior networks paper already. I think it's very promising, and this goes back to the question of there's still like a lot more headroom on how do we improve the single model that we use. And from probabilistic modeling, you can think of this as, parameterizing like using the conjugate priors idea, and you parameterize a more flexible distribution, and those design choices can improve performance. And our hope is the baselines that we open source will allow us to also investigate a lot of these other ideas that perhaps people haven't put together as much in combination with other methods already. So yeah.
Maybe, what do you think are the downsides of these methods, basically?
I don't think it's a downside of, in terms of like parameterizing like discrete distributions versus Dirichlet, I don't think there is any necessary downside necessarily on top of that. But there are some papers, I don't remember which off the top of my head, but they kind of do two things. One is they introduce the Dirichlet distribution, but sometimes they also assume access to some known OOD, and they may tune the concentration parameter on top of that. But that could potentially, if you don't have access to like other data, that could be a limitation in some settings. It may not be always possible to define for all kinds of like input distributions, like this notion of others. So we need more like, so in those cases, we may want to maybe like, disentangle the contributions that you get just from parameterizing as a Dirichlet versus like, using the knowledge of like extra data and so on. So, but that's not to say again, like, it's not a criticism of the Dirichlet, parameterizing it as a Dirichlet itself. It's just like, I don't see any, because it does include the discrete distribution as a special case. So if you do believe, barring any optimization issues, it should at least recover the base model, right? Like, so I don't see any obvious downside.
I think there's an upside that's interesting, which is like the Dirichlet does concentrate in maybe in ways that you don't want, but like there's a whole family of distributions that may be the thing that you do want, like a Pittman-Muir or something, if you think your data is really heavy-tailed or long-tailed. And so like maybe the Dirichlet is not the right choice, but there's kind of a whole family of things that you could replace it with from the kind of probabilistic toolkit that could build more expressive models.
Okay, thanks a lot.
Okay, Disha, do you want to go next?
Yeah, hello. So my question was that so will you say that out of distribution generalization is different from adaptation or approaches in transfer learning like multitask learning or meta learning and stuff like that? So that is my first question. And the second question is that do you see length generalization and like compositional generalization as cases of out of distribution generalization? If yes, then are there any specific approaches which are dealing with this specifically?
So I can take a stab at that. So I think there are a few areas that all tackle all sense of distribution shifts. As you say, there's transfer learning, which is closely tied to meta learning. And if you assume that you can train on the data, there's multitask learning. There's also causality, so you have explicit interventions. And there's like out of distribution robustness, and there's adversarial robustness. I think I just named 6 fields. I think they all tackle slightly different things. For the specific distinction between transfer learning and out of distribution robustness, I think the major ones are, one is zero shot. So in the sense that you train on a specific data set, you evaluate, and you don't really adapt to whatever you're evaluating on. So there's no fine tuning aspect of it. I think another aspect of it is the sort of input and output domains that you're transferring on. So if you do image classification on ImageNet, you're still going out of distribution robustness, so you still assume that the image resolution you're predicting on is still 224 by 224 or 256, I forget. And then the output is still 1,000 classes. So transfer learning is usually about different tasks, so you might have different input-output relationships. I think ultimately, however, they're all extremely important, and I think the methods that are all used across these different areas are all extremely related. And if you have a good understanding of that overall set of 6 different fields, then you'll have a good understanding of being out of distribution robust. So there's that. I think another point you asked is compositional generalization. I do think compositional generalization is an important aspect of OOT robustness. I think that also most closely ties to causality, in that if you know how individual semantic objects and shapes, textures, all that sort of things compose together, then you ultimately are learning more about the semantic behaviors, just that you're robust to arbitrary shifts. Some useful maybe benchmarks that are there, at least in the OOT robustness literature, are there's a shapes versus texture sort of work. So there's like a stylized ImageNet. There's ImageNet R, which is about different renditions of ImageNet with different backgrounds and foregrounds. There's also this specifically called, like with using the term compositional generalization, does work from NLP on changing out different word meanings and different actions, such that maybe the meanings of the sentences are very similar. So I think that there's tons of ripe areas in terms of evaluating on things like compositional generalization.
Yeah, just to add to that, I think all these questions are very related. The question of generalization in particular on all these ideas, I think would work very well with a lot of the topics that we spoke about in the tutorial. Going back to the first question that you were asking, I think I guess the point we are trying to highlight is you can think of it as a whole spectrum in some sense. So there is something about, there's only this data set that you train on, but at test time, you might be asked to predict on a different distribution. So there is this, you can think of that as a detection question, to just recognize that this may be a different distribution where the model is more likely to be wrong on those data and calibrating the probabilities accordingly in some sense. So there is that detection question, but then you could imagine in a practical system, maybe if you detect you're doing a lot of mistakes, so maybe you may want to kick in some sort of like adaptive retraining, and there's this whole spectrum. You may assume some access to like, some unlabeled examples from the domain, and they have done some work as well showing that, adapting batch norm statistics to the on this domain can significantly improve performance under some settings. But you can also assume like, a small label set from that, and kind of like fine tuning and adapting that, transfer learning and domain adaptation and so on. So those ideas become important. But I guess the first question is being able to recognize that this may be a different distribution where you're likely to be wrong, and not making a confident wrong prediction and recognizing that you are likely to be wrong. And I think that detection part is probably, that's the, let's say, the distinctive part in the tutorial compared to some of the other literature. But it's not to say we can't combine these ideas together. Like once you detect, then how do you deal with it? And you can do domain adaptation, and there is a whole spectrum of ideas that we can do there. Yes. In the interest of time, I think we should go ahead and maybe take one last question. Cornelius?
Yeah, and there's a couple more in the panel that I think are worth answering, but I think they're quick, about baselines and...
Hey, thank you very much for talking to us. I was just wondering, I'm coming into this from a more applied perspective, namely healthcare. I was wondering, there are lots of advancements on certain uncertainty measures, and they have nice properties, for example, mutual information for active learning. What is the state of the art for interpretable uncertainty measures, for example, for doctors and nurses to use in clinical practice?
From the interpretability perspective, I'm not aware of actually the work in the literature on like evaluating uncertainty estimates directly from interpretability in this particular setting. But I think I agree it's an interesting research question. It'd be nice to do more of this, and deploying uncertainty in the loop, and kind of identifying whether what people find most helpful and so on.
Yeah, this is definitely in the domain of Bayesian hierarchical models, right? Like much simpler models, but if you turn the crank on these, then often the interpreting the parameters is meaningful, because the models are identifiable as well. And deep nets don't really lend themselves well to that.
Yeah,
I think there is some work on the interpretable deep learning. I think there was a tutorial, and I know one of the presenters, Hema, has done a lot of work on at the intersection of uncertainty and interpretability. So maybe it's worth looking whether they have done some work on in this space. I'm not aware. Sorry.
I think of interpretability sometimes a moving goalposts. I like some of the work that I'm a huge fan of, that maybe shout out for interpretability is sort of looking at like input output relationships. So ultimately, if you're trying to do this specifically for practitioners, they may not be super interested in understanding the internal aspects of the model, because they may not have that expertise. But maybe they do have the expertise, so they do want that. I think there are some works characterizing, for example, exemplars that are effectively determining the overall set of examples, that like different example behaviors that a model may make predictions on. I think looking at the distribution of just the predicted probabilities is very helpful. So even if you don't know how the model is performing, just looking at those probabilities, which is more downstream, can help a lot. I think ultimately there is a lot of work in attribution, exemplars, understanding sparsity patterns in interpretability that can make tons of headway. And we haven't made. I don't think there's too much work in this intersection just yet, but I think it's very right to do so.
Thank you very much.
Yeah, there's a couple questions in the panel. Balaji got to one. So Dustin, maybe you want to take this one from Jordy or Yordi. How are you planning to extend the uncertainty baselines? And how can we contribute either on the methods, evaluating proxy setups, or benchmarking side?
I think there's we over the past year, we've been continuing to stress test the different baselines. Like we've set up a canonical task. We continue to apply a bunch of different methods such that we're really confident that these are the strongest baselines for these tasks. I think in terms of extensions, on one side, it's better reproducibility, making sure that the things we have can have error bars or report over 10 different seeds, stuff that we currently do, but we need to make sure that external folks can actually, in fact, reproduce these things. So we've been verifying these on like cloud CPUs, on different hardware. I think another aspect of it is adding more real-world benchmarks. So if there's interest in the community around something like a large-scale regression benchmark, to really make sure that we're making meaningful progress on uncertainty for regression, I think we should all collectively sort of discuss like what a good example for regression would be. I think on the question of how to contribute, what I would recommend is either raising an issue on GitHub, or you can even reach out to the lead, Zach Nato. I think it's znato@google.com. And we can definitely just set up a meeting, one-to-one meeting, or one-to-one-to-one or something, meeting, and sort of discuss like what are the things you're interested in, how can we best prioritize them, how can you best contribute. And I think we're super open. In any ultimate white paper that might come out, we'd be happy to add anyone who contributes.
I think we should probably stop there. Yeah, I think we answered most of the questions.
Yeah, well, pressing. Maybe you could put it in the Rocket chat and we can try to check it out as NeurIPS goes.
Yeah, thanks for all the awesome questions. I think it was great discussing, and very nice to see a lot of excitement in the community around these topics. And yeah, if you have questions, we will continue to monitor Rocket chat. If you have questions or other things, so please post your question there and we'll be happy to answer. Thank you, everyone.
Thanks, everyone.
Yeah. Thanks.